Okay, so Michael, let's start now. It's 8:30 here.
Absolutely. Go right ahead, Tajender.
Okay, great. So good evening, everyone. Very nice to have you all with us once again. And it gives me great pleasure to welcome David Chester to give the 15th OSMU lecture on physically realistic minimal models from E8. David is presently with quantum gravity research in Topanga, California, where he's a research scientist working on aspects of quantum field theory, general relativity, quantum gravity, and the Standard Model. David obtained his BS in physics from MIT and his PhD from UCLA in 2018. For his PhD, David worked on scattering amplitudes for Yang-Mills theories and computation of gravitational radiation from Feynman diagrams. In recent years, David and collaborators have been actively researching on E8 octonions and their application to fundamental particle physics and gravitation. David's YouTube video on E8 is very informative and useful, and today we will hear more about his insights on what we could call the king of exceptional groups. Great, David. Go ahead.
All right. Thank you very much for the introduction, Tejinder, and I appreciate all the organizers for the invitation. Yeah, so today I'm going to talk about physical applications of E8, striving for minimal models. And so let's see what we got. So, well, we're here at this OSMU conference. So in order to talk about these things, we should first specify what the octonions are and how they relate to E8. And we'll also talk about what the standard model is and what unification means. Now, starting with unification, we know that we have the standard model with three forces of nature and general relativity. Now, if we just add these two in an action, I wouldn't call that a unified theory. We want something deeper than this. Now, Einstein obviously was one of the first proponents for this, as well as Weil. And there's a nice history there with Einstein, and he actually discovered metric teleparallelism, which was merely a theory of gravity. And there's been some recent work that has figured out how to use the non-metricity for electrodynamics. I'm not going to go into that today, but that's one route for unification. But typically, usually people in quantum field theory talk about unifying the interactions because we have all these different forces and they have different coupling constants. So if we could find some gauge group that can bring all of those forces together, then in that sense, we could get a unification of the forces. And maybe along the way, we might also find that the fermions get a more natural origin story as well. So one idea that will be a big focus of this talk is how a single E8, I should say Lie group in this case, can have a representation for all the fields in the standard model and GR. So typically in quantum field theory, people will take representations and add them together based on the gauge group. But here we're trying to see if we can use a single representation to encode all of the fields that we see. So what is E8? Well, E8 refers to multiple different related objects. So there's the E8 Lie group, which is this 248-dimensional manifold. And that corresponds to the E8 Lie algebra, which has the 248 generators. And this can all be described by the E8 root system. So if you take 8 Cartan generators, that gives you a basis for this 8-dimensional root system. And then you'd have 240 root vectors left over. And there's also other things such as the E8 Cartan matrix, Dinkin diagram, lattice, and obviously all these things are related. So it's just worth to keep in mind when we say E8, there's actually multiple things that we could be talking about. And so obviously for this conference, we're going to be very interested in how the octonions relate to E8. And I would say there's really two main ways, at least, that the octonions relate to E8. First, we can have the octonionic root system. So we know that the E8 root lattice is in 8 dimensions, and it's very convenient actually to take the root vectors and express their coordinates with octonions. They have nice multiplicative properties as well. And so we can also use the octo-octonionic Jordan algebra and maybe take nested operations, kind of like what Cole-Fury does, and actually Wilson-Drain-Minogue as well. And so that's a completely different way to relate the octonions to the E8 Lie algebra, because this is more referring to the 248 generators rather than the 8-dimensional root system. And I should also mention there's many ways you can construct the E8 Lie algebra. You can construct the algebra itself from the lattice. You can use octonions, as we'll talk about. You could use CL16, or you could actually get it from SO248 as well. And so I think 2023 is really an exciting time for octonionic physics because there's been some serious mathematical breakthroughs that have happened last year, in particular from Wilson, Dray, and Minogue. They've really started to figure out how we can use these octonions to implement the E8 Lie algebra, which is very exciting because it's going to open up a whole new paradigm for applications in physics. And so just to go into the history a bit deeper about this relationship between E8 and octonions, there was work from Rosenfeld, and eventually this led to the Freudenthal-Tits construction, where you use derivation algebras of octonions, and you can combine that with Jordan algebras, or maybe the traceless part of a Jordan algebra with some imaginary part of octonions, and those give you representations of G2 and F4 to describe E8. And there's been other octonionic relationships as well, such as Barton-Sudbury, as studied by Coogan and Townsend, as well as the more recent construction from Wilson, Dray, and Minogue. So just to give an overview of the Freudenthal-Tits construction, we have these exceptional Lie algebras, and if you take the derivations of the octonions, you get G2, which is the least exceptional Lie algebra, and then J30 is the exceptional Jordan algebra, and the derivation algebra of that is F4. Now, when Freudenthal and Tits were trying to make sense of Rosenfeld's work, they realized that if you combine alternative algebras with Jordan algebras, they were actually able to find a Lie algebra in this manner. And a good example of our alternative algebras include all of the division algebras. So in this manner, we can actually construct F4, E6, E7, E8 in terms of this Freudenthal-Tits construction by running over R, C, H, and O for A, and then taking B as being O. Or you could also take A as O and then take B as being R, C, H, and O. So I'm not even going to show the full table, but you can fill out this Freudenthal-Tits magic square, which clearly shows how the octonions are related to the exceptional Lie algebra. So basically, there's a bunch of non-interesting stuff in here because we're obsessed with the octonions, right? And so we have F4, E6, E7, and E8 coming in, where in the corner we have the octonions relating to E8. And so this really does provide a solid motivation for the study of the tensor product of the octonions with the exceptional Jordan algebra for understanding the structure of E8. Now, this originally was inspired by Rosenfeld, who was thinking about generalizing projective planes to understand how to make contact with these exceptional Lie algebras. And this led to some controversy at first because he claimed to prove it, but the proof was never published. Now, it turns out that Atsuyama actually proved it in the early 1990s, but this was largely overlooked. And in modern days, Baez has certainly popularized these ideas. And so the basic idea is that if we have some Lie group G, we can find some subgroup H and then take some quotient space Q that would just mod out G by H, which would remove the generators of H from G. And this actually can give us some projective geometry where the generators end up corresponding to this manifold. And we find that for F4, E6, E7, and E8, when you mod out by these different groups, I actually just put the bar over here just to fit it in the table. So that's spin 9, spin 10 cross U1 is inside E6, spin 12 cross SU2 is in E7, and spin 16 is E8. And when you mod out by these H's, you get these different projective planes. And what's really interesting about these projective planes is that they're spinor representations. And so besides spin 9, because of triality, besides that one example, the exceptional Lie groups are the only examples where the adjoint representations contain spinor representations. And that's very interesting for us because us physicists want to use spinors to describe matter. So I'll just briefly mention that I've collaborated with Daniele Cordetti, Alessio Morani, Ray Ashheim, and Clea Irwin on a few different topics relating to the exceptional Lie groups. These are mostly mathematical papers, but this one right here is also a physics paper. And so I'll just briefly discuss that work a little bit. Well, I'll build up to it. Right, so we have these Freudenthal-Tits constructions that give us Lie algebras. And we realized that out of all these different constructions, this one seems to be the most general because it allows us to work with alternative algebras. And so this actually allows us to apply it to C cross H cross O. And we were able to find some new Dixon-Rosenfeld projective lines is what we were calling them. So we can look at C cross H and take that and tensor it with J2O, or we can look at C cross O and tensor that with J2H. And these are different. And then we could also look at O and tensor that with J2C cross H. And so we found that these were the only three sensible possibilities. And we were also able to take the physics of Colles-Fury and uplift it into this projective line geometry. And maybe you could guess where we're going to go next. We've developed the mathematical results. I just got to find the time to finish it. But basically, we can also construct these Dixon-Rosenfeld projective planes that would provide, basically what I'm trying to do here is take what I've learned from E8 and see if I can apply it to Colles-Fury's her physics to see if we can get a new way to get at 3 generations. So that's still a work in progress, I'll just mention. And so another thing that I realized as we were looking into this is that there's actually a way to relate E8 and C cross H cross O mathematically into some even larger structure. Because in some sense, the most exceptional Freudenthal-Tits construction could use C cross O with J3O. And note that the split octonions get used in E8 minus 24. I'll talk about this in more detail in a bit. And this can be, the split octonions can be embedded in the bioctonions, which is a tensor product of the complex numbers with the octonions. And so we see that right away, this E8 minus 24, this non-compact real form of E8, should be inside of this most exceptional Freudenthal-Tits construction. On the other hand, we know that C cross H obviously fits inside of C cross O. So it's not too surprising that we could get C cross H cross O to fit in C cross O cross J3O. And so in this sense, we see that this most exceptional C cross O cross J3O, this most exceptional Freudenthal-Tits construction, in some sense, could bring together the physics of Colles-Fury with E8. Now, I'm not suggesting that this mathematics is what we should pursue for physics, but I think it's mathematically interesting, so I just want to point that out. Now, I also wanted to just briefly mention the construction from Wilson, Dre, and Minogue because it's so amazing, to be honest. And just to provide some historical context, Feza-Gursey was a pioneer for understanding how to bring the octonions into physics, and it's understood that we should apply octonionic matrices to make contact with this. But they were able to nail F4 and E6, but really, out of all of the researchers I've talked to, I only know so many, but a lot of people got discouraged about using octonionic matrices in the 1970s and 1980s. For instance, Pietrini said this was completely a fruitless goal. But despite that, Wilson, Dre, and Minogue were really able to make some serious progress last year. And so this allows for us to use octonionic matrices to take the Lie algebra transformations. I should also mention that Feza-Gursey is really just an exceptional physicist who has really bootstrapped a lot of the mathematics and the physics for the applications we're interested in. However, I will point out that their 1973 paper, which mentions octonions, it talks about ST3 and G2 as being the automorphism octonions, but then they use the split octonions for quarks. Gursey was also helpful for constructing E6 gut and most likely influenced Bars and Gunaydin on their work in E8 gut. And for understanding how to go beyond the standard model, I think Gursey was the first to point this out, is that if you look at the EN root systems and compare them to the Lie groups, it turns out that E3 is the same thing as A2 plus A1, which would correspond to SU3 cross SU2. Now, this isn't the full gauge group for the standard model, but U1 has no root system, so in some sense, that's the best we could get. And E4 actually is the same as A4, which gets used which is for SU5, which is a common gut group. So E5 corresponds to D5, which is spin 10, another gut group, and E6 is a common gut group, and obviously E7 corresponds to the E7 Lie group corresponds to the E7 root system, and similarly for E8. And my perspective, I put this in parentheses because it's really my perspective. When you study E7, you start to realize that it contains the states for E6 gut for 1 generation, whereas E8 seems to be nice for 3 generations. So it's very important for us to consider the difference between compact and non-compact algebras, generators, all these things. And I think it's led to some confusion in the field, really going back to the work of Goodnight and Versii in 1973. And in my opinion, they kind of imply a mathematical error because they talk so much about the octonions, but then they switch to the split octonions. And it's very important to mention that G22, which is the non-compact real form of G2, as the automorphism group of the split octonions, it does not contain SU3. So if we're going to use the octonions and claim that the split octonions, I should say, and claim that the automorphism group is relevant for QCD, well, that doesn't work because QCD is described by SU3. And you can get to SU2, 1 or SL3R, see the work of de Graaf and Marani. But the thing is that it's just not what is used for QCD. And the pioneers of QCD were well aware of SL3R, and they've published papers discussing SL3R in relation to hadronic models. But the role of SL3R, due to its non-compact nature, it makes it different than SU3, at least in terms of what these authors were seeing at that time. So I just figured I'd mention those works. And so in this talk, I'm really trying to motivate that the split octonions are more relevant for 3 generations of matter than QCD. So that's going to be a common theme throughout this talk. And just to elaborate on this a little bit, I should probably work through the details here at some point, but this is a conjecture of mine that if you basically take all of the physics we know and love with complex numbers, we know that SL2C gives us the Lorentz group, and we can take the conformal group of SU22. If you just take that C and replace it with the split quaternions, it gives us some nice structure to make contact with some of these Lie groups that have applications for 3 generations of matter. And basically, the intuition here is that the extra time dimensions are for the extra mass generations. And so it's not actually as exotic as it sounds. The extra time dimensions aren't really changing our perception of time. And I'll show you why in a little bit. And so once you can conjecture maybe that SU22 over the split quaternions might relate to spin 4-4. And there's some evidence for this because there's compact realizations of this isomorphism that have been pointed out. But it's definitely understood that if you just take the split octonions and you consider nested multiplications, you can get to spin 4, 4 as well. And I'll also point out that I'm not the first person to claim that spin 4, 4 would be useful for 3 generations. Bertram Constant pointed this out when he considered the intersection of spin 4, 4 with SP8R, which you could think would be for relativistic phase space applications. And he pointed out that this gives 3 charts of U2, 2 or SU22 cross U1, which is for the conformal group with an additional U1. And triality has also been used by Furry and Hughes recently for the Higgs boson. So we're thinking of extending triality to the split octonions. And in this talk, rather than focusing on SP8R, we're going to focus on SU32 because it's in E8 minus 24, and it intersects with spin 4, 4 to give us the same 3 conformal charts. And this is very interesting because we can use this SU32 for gauge symmetry. And so we're going to be trying to understand that basically there's tension between isolating spin 4, 4, and gauge symmetry, but taking this intersection helps dispel that tension. And so we should also briefly mention what the standard model is. Well, it's this Kyle gauge theory. It's got SU3 cross SU2 cross U1 symmetry. It uses compact gauge groups. And note that all of the electric charges in the standard model, including the right chiral fermions, are coming from charges of the representations of SU2 cross U1. So this is very important. If you're going to get the standard model, it has to work in that way. That's just how it's defined. And so here we can just review the Lagrangian for the first generation of fermions that would include a neutrino, 3 up quarks, the electron, 3 down quarks. And here is just showing the fields, and here are the representations corresponding to those fields. So if we had the quarks in some weak isospin doublet, there's also going to be a color triplet, and it might have some weak hypercharge. And obviously, you can also take a covariant derivative of these fields, and those would encode the interactions and include the charges, where basically the representation theory is figuring out what goes into this covariant derivative. So the representation theory is going to be very important for deriving all of this physics. I'm not even going to go into details here, but you can get a Higgs scalar and Yukawa couplings. And basically, there's all these different commonly studied grand unified theories that can bring together the standard model. And the structure to pay attention to is that E8 can lead to E6. You can also get an SE3 for flavor symmetry. E6 contains spin 10. You could study spin 10 gut or flipped spin 10 gut, which would include the extra U1. There's SU5 gut or flipped SE5 with an additional U1, and there's the petit salon right here, all of which can lead to the standard model. And there's trinification and a few others, but those are the main ones. And so some of the research questions we're going to be interested in answering here today are basically, how can we fit the standard model with general relativity into a single representation of E8? How can we get 3 generations of matter to fit inside the 128 spinner, the Majorana-Weil semi-spinner of E8? Can we actually fit 3 generations in there? That's been a difficult challenge. And how can we get these complex chiral fermions in D equals 3 plus 1 to emerge from this Majorana-Weil spinner? Another thing we'll be interested in understanding is, what are all the different gut models with gravity that we can find from E8? And really, it'd be nice not to just classify all the possibilities. We want to just focus on one explicit model. And so really, I want to stress that the model I'm going to present today, it's not the best model by any means. It's just one concrete model. There's still a lot of work to be done. And so overall, the point of my talk is not to claim that I've figured everything out or anything like that. I really just want to say that I think it is possible to use E8 for applications to physics. And hopefully this will open up the door to allow for a lot more exploration in future work. And so really, as you can see, I've only put out one paper so far discussing E8. We put it on arXiv in 2020, and it got published by 2023. And it should have actually been called Beyond the Standard Model with 60 twisters or pseudo twisters. But I actually call it 60 spacetime at first, then we change it to spinners. But really, it's about 60 spinners coming from spin 4,4, because that would be the conformal group of 6 dimensions with 3 time dimensions. And so we're almost done with this paper right here that will talk about minimal field theory from an exceptional superconformal multiplet. And I'll show all the results from this paper today, and that should be out very shortly. And so it's important to understand the fundamentals of representation theory for all this, because this is going to be useful for defining the fields that we have and showing us what charges they have and determining all the interactions in the theory. And so conservation laws motivate continuous symmetries, and these motivate representations of these Lie algebras. So if you took a direct product, a direct sum of different Lie algebras, you could get different representations with respect to all of these different Lie algebras. So if you had G1 through Gn, you might have some representation, R1 through Rn. And if you had some U1 or spin 1,1 Lie groups, then those could have charges or weights associated with them. Sometimes people put these in the parentheses, but we'll put those as subscripts. So whenever you see representations with subscripts, that's going to refer to some U1 or spin 1,1 charge. So one simple example, that if we had SE3 plus E1, we might have some quark with some U1 charge as shown there. And so when we go into exploring Lie algebras, really the classification of Lie algebra is a big part of why this is explored, is because it was understood how the division algebras would relate to these Lie algebras through understanding their defining representations. So we have matrix algebras over division algebras, and that gets us pretty far to exploring a lot of different Lie algebras, especially for the exceptionals, because we can only go up to 3 by 3 because there's OP2, but there's no OP3. And so we can get pretty far, as I was saying. So if you look at U1 over the division algebras, I should probably call this A1 because there's unitary, but once you start getting into the division algebras, it's actually helpful to use anti-unitary. So that's why I wrote SA to A. And so if you can get SO2 from complex multiplication, that's more well known. And the quaternions can give you SO4, whereas the octonions can give you SO8. But if you embed these division algebras in 2 by 2 matrices, you can start to get things such as SO2, SO3, SO5, SO9, and then you can actually consider SL2A. For instance, SL2O can give us SO91. But if we continue further to 3 by 3 matrix groups, then we can get to the exceptionals. Now, if we only use just the octonions, we can get to F4, and if we try a little harder, we can get to E6 through results from Dre and Minogue. But if you actually consider tensor products of A and O, as we were mentioning with the Freudenthal-Tits construction, then we can get to the exceptional Lie groups here. All right, it's a little slow there. All right, branching rules. So when we have these representations, what we're going to want to do is consider some Lie algebra and its subalgebra H. So we have G that might contain H, and G is going to have some adjoint representation associated with it. For instance, G2 has 14 dimensions because its adjoint representation is the 14 representation. And so we can isolate SU3 as a subalgebra inside of G2. And that means that we're going to have the adjoint of SU3, that's the 8 representation. But we need other representations to add up to the total adjoint representation of the original algebra. So for G2, we find that we get, when we break to SU3, we also get this 3 and this 3 bar representation. So that's just one example. And we can go through and classify all of the different real forms of the exceptional Lie algebras. And F4 has 3. And it has F4 minus 52. And this number here is the number of non-compact minus compact generators. It's a convention that physicists have developed. So this compact real form of F4 has SO9. There's another non-compact real form of F4 that has SO81, and yet another that has SO54. And I'm not exhaustively showing all of the maximal subalgebras because F4 minus 20 also has SO9, but these just kind of show you some of the different structures that you can get. And here's just showing the commutation relations for F4, just why not show it? But let's move on to the real forms of E6. There's actually 5 different ones, and so the compact real form of E8 has SO10 with U1, but there's other non-compact real forms of E6 where you can get SO91, SO82, SO64, and SO55. So it's really interesting to see how all of these different things can relate to division algebras and split division algebras as well. So you can have, if you use the division algebras, that's typically going to make contact with the compact ones. Well, it depends. Sometimes you can get to these if you use the SL30 or something like that. Then that'll introduce a non-compact structure. But basically, C and H and O are more compact, whereas the split division algebras are non-compact. And so when we move on to E7, there's 4 real forms for E7. And the compact real form has SO12 with SU2. And there's also other ones with SO10 too. So maybe that would have applications to the conformal group and D equals 9 plus 1 if you're into that type of thing. And we also have other non-compact real forms with SO84 and SO66. And some of the SU2s get changed as well. And so once again, you can take quotient spaces by removing these parts and you get spinors that remain. So the nice thing with all these exceptional Lie groups, when you isolate the orthogonal groups inside of them, with the orthogonal algebras, then what is left over oftentimes helps isolate the spinor representations. And finally, for E8, there are 3 real forms. The compact real form has SO16, and the quaternionic real form they called, or half compact, this is E8 minus 24, that has SO12-4. This is going to be my personal favorite, especially for this talk. And there's also E88, which has SO8, 8. And so we all 3 of them have these 128 spinors. These are real Majorana-Weil spinors in 16 dimensions. And this isn't even the exhaustive list of all the maximal subalgebras of E8 minus 24. These are just the list of ones that I've identified that might have some physical applications. So we can look at SO12-4. There's also this SO16 star. I won't really talk about that. There's SU7-2. This one is actually quite curious. I like this one a lot. There's SU6-3. Maybe there's some utility there. And the star of the show today is really going to be SU32 plus SU5. This is really amazing to me just because it's a maximal compact subgroup that immediately gets you to SU5 and seems to have something that immediately hints at structure for 3 conformal groups, because it's very obvious to see how there's 3 different SU22s inside of SU32, and we're trying to understand how can we get 3 generations out of E8, and we want a gauge theory. So resorting to spin 4, while it's very nice because it relates to octonions, it's not the most helpful thing for gauge symmetry. So this one is really going to be the star of the show today. But there's other maximal algebras that could be explored. There's also SE41 that can be found, and various different E7s can be found. This one is also interesting, the E62, because it isolates an SU3, and that could be used for color for QCD. So this one's pretty curious, but I'll take the more conventional route of unifying the standard model first, and then bringing and trying to think about how to bring gravity with the standard model or grand unified theory together after. Whereas you can see E6-2 would leave QCD out of the story for a longer time, which would be interesting to explore, but I decided to choose to explore this first. And finally, there's also this F44 with the compact real form of G2, which also could be pretty interesting. All right, so just to give a lightning overview of the history of E8 and its applications to physics, really, I think the first example of this goes back to Bars and Gunaydin in 1978. By 1980, they introduced this E8 gut model, which had a 3,875 Higgs field, had no gravity. And so it's this behemoth of a theory. And really, there's a problem once you start introducing too large of Higgs fields, people start to think, well, maybe this isn't real. But there's actually also this other theory that came out in 1980 by Conjecture that considered this supersymmetric E8 gut that used a 248 Higgs. So I've never actually calculated the differences between these Higgses and looked into the implications. It looks like some people are claiming that you can't use these Higgses to break the symmetry because you can't get complex representations out. I'm not sure if that's true or not, but basically, overall, it doesn't really matter because what we're going to be doing, we're not going to gauge E8. So we're just trying to understand how to use E8 to get all the states. So all this complications with if there's problems here or not are not really relevant for us. But anyways, moving on, basically the string theorists and supergravity research kind of dominated all of the math and physics research for E8 for quite some time. It got used in supergravity a lot because you could find E8 in applications to U-duality. Eventually, E8 cross E8 heterotic string theory got developed, right? And really, Ed Witten's M theory was inspired by trying to make sense of heterotic string theory. And also, they wrote some papers describing how M theory is an E8 gauge theory. Peter West has talked about even up to E11 as being useful for M theory, and Gunaydin, Kopsel, and Nikolai have also talked extensively about the applications of E8 to supergravity. So there's a lot of rich mathematics here that is worth learning about from these authors. Even if we aren't interested in these physics theories, just the fact of the matter is they figured out a lot of the stuff that we need to understand. Also, I should mention that Adler wrote a paper or two on E8 around 2002 to 2004, and he really hoped for applications of E8 to 3 generations and supersymmetry. And this is going to be a big topic that we're going to talk about today. We're going to show how to turn E8 into a superalgebra. All right, there we go. So Bars and Gunaydin, as I was mentioning, had this E8 gut, and they had this other paper that discussed ternary algebras and superalgebras. And this was just some approach they had for studying Lie algebras, but they considered turning super Lie algebras into Lie algebras, which is very curious because these guys were the experts in exceptional Lie groups. And the exceptional Lie groups contain spinor representations, just as super Lie algebras do. And so for whatever reason, I just find it remarkable. They talked extensively about how to turn super Lie algebras into Lie algebras in a paper that was very focused on exceptional Lie groups, but they never thought about turning it backwards, turning it the other way, and turning exceptional Lie algebras into super Lie algebras. And so that's something that we'll talk about in a bit. And another big breakthrough, or I guess another big pivotal moment in E8 physics, obviously, was when Garrett Lisi came out with this paper in 2007. And it had a lot of problems. Let's be honest. It was inspirational to some of us, but there was a lot of issues. There was no rigorous identification of the chiral fermions, let alone 3 generations of fermions. It was just sort of speculated that maybe, it was suggested that maybe it could be used. The original paper mentions spin 15.1, which is just crazy because there's no real form of E8 that contains spin 15.1. I mean, maybe you could argue that he's saying, oh, he's taking a Wick rotation, but he didn't even say that, right? That would have been the easiest thing to just state, hey, we use the compact real form of E8 and we Wick rotate. But he didn't even say that. He claimed to have a super connection. In order to have a super connection, you need a superalgebra. So he didn't have that. And so it was just really hard to know what to do with all of this work. But he came up with another paper in 2015, which in my opinion was way more inspirational because it focused on this non-compact real form of E8, but it focused primarily on spin 4,4 and spin 8, which obviously has its relationship to the split octonions and the octonions, but there was no rigorous derivation of the gauge theory and no explicit realization of free generation. So it still was highly problematic, but we can still take something from this and see. I mean, he saw this vision, and that's the vision that I'm after as I try to go to this next slide. All right, so this is how I'm going to formulate Garrett Lisi's dream. There's two incarnations of the dream. Basically, the dream, roughly speaking, is to get the standard model in gravity from a single representation of E8. The strict version of that is to construct a theory that only has 248 off-shell degrees of freedom. I'm not going to talk about that today, but there's another way you could do it where you just use the 248 representation. And if you take a subgroup of E8, you could gauge that subgroup. And if you're going to gauge that subgroup, it's going to be associated with some spin 1 vector bosons. And so those vector bosons, let's just say you pick SU32 cross SU5. There's going to be 24 plus 24. There's 48 generators associated with that subalgebra, but you're going to have to multiply a vector, a 4 vector, times that 48 to get the vector gauge boson. So in this theory, when you gauge a subalgebra, you're going to have more than 248 off-shell degrees of freedom because you're going to have some vector bosons, but you're only using the 248 representations. So that's kind of the picture that I'm going to be talking about, is this looser realization of Lisi's dream, let's say. And so we want to figure out what real forms of E8 do we want to use. Basically, I like E8 minus 24 because it's slightly non-compact. It gives us just enough room for gravity, yet is mostly compact to give us a good chance of making contact to compact gut. And originally, I thought it wouldn't even be possible to use E8, but very recently, I've realized that maybe, oh, actually, this should say SU32 cross SU32. So SU32 cross SU5 is in this E8 minus 24. There's a typo here, but E8 has SU32 cross SU32. And it's actually similar to Tegender's models because he likes this idea of getting two E8s. Well, if you simplify that to two SU32s, that would be an E8. And the X and Y bosons that lead to proton decay would become non-compact. So I don't really know, but it would be curious to explore this for proton decay. And actually, it was kind of inspired by conversations I had with Eric Weinstein. So let me try to move to the next slide. It's a little slow. There we go. All right. So we're going to try to understand how to get gravity and gut from E8 minus 24. So really, we're going to understand how can we get representations with respect to the Lorentz group with the standard model. And we'll talk about all of these different gut models as well. I just need to get going because of time. So basically, you can get to spin 10 through spin 12-4. And various different authors, such as Tony Smith, Lisi, Garrett Lisi, Krasnov, Carlos Castro, they've all discussed these things to some degree. Krasnov has discussed spin 11-3, and Bars discussed this in the supersymmetry community as well, but they had slightly different applications. Ward also mentioned spin 14 star. So that's one way to go about getting SO10 or spin 10 from E8 with the conformal group or the Lorentz group. And then we can figure out what are all the ways to get to SU5 that do not go through spin 10, because obviously we can get SU5 through spin 10. Well, you can also get it through SU72 and SU32 plus SU5. So this is very interesting. There's 3 different ways to get to the conformal group with U1 and SU5. You can get it through spin 10 directly, or you can go through SU72 or this one. And Alessio pointed out that I said these are the only paths. I missed one through SU63 as well. And there's also other ways to get to Petit Salon that don't go through spin 10 as well. I'll just put them on the screen here and briefly mention them. And there's also ways to get to the left-right symmetric model as well. But that's not going to be a big focus. The big focus for this talk is that there's 3 paths that lead to SU5 with the conformal group with an additional U1, as I was mentioning. And I just find this fascinating. And all of the representations work out to be the same. So that was the main result that we found in that 2020 paper. And so now we want to move on to understanding, well, really some work from Piero Chiarini, who he did some work with some of my collaborators. And what he had this really nice effort where he was considering this 12-dimensional lattice model that included spacetime outside of E8, and he was working with a sociohedra. And he introduced this Grassmann envelope of E8, which turns it into a super Lie group. And that's really the insight that I'm going to focus on the most. I found this fascinating. And so basically, there's some history here because Bars and Goodine, as I was mentioning, they mentioned how you can turn super Lie algebras into they mentioned, yeah, how to turn super Lie algebras into Lie algebras, but they didn't do it backwards. And so Shestakov had some work where she talked about this Grassmann envelope, and then Piero Turini realized that you can use it to force it the other way around. So you can get some anti-commutators to come. If you have some commutator algebra, if you basically introduce some Grassmann parameters and associate them with the generators of, let's say, the spinor representations of E8, you can turn it into a super Lie algebra. And so, for instance, we could take E8 minus 24, and it would have rotations in 16 dimensions of signature 12,4. And so you'd have 120 generators of this J. And let's say T was the 128 spinor left over. And this algebra would have commutation relations with everything are commutators, and you could use gamma matrices from D plus 12 plus 4 to implement that. But the thing is that it's not a super algebra. But if you use this Grassmann envelope, you can get these generators Q that would anti-commute and have the same relations. It's just anti-commutators instead of commutators. And so what we've been doing is trying to understand what are the minimal classical Lie superalgebras that contain this Grassmann envelope, which we'll use gamma to denote the Grassmann envelope. And it turns out it can fit into these classical super Lie algebras, which is pretty curious. And so now we're going to be interested in this SU32 cross SU5 inside of E8 minus 24. And then we're going to want to take the Grassmann envelope of all this and understand what's going on in that super Lie group. But before doing that, it's just worth showing the representation theory. So when you break this 248, you get the 24 vector bosons of SU32 for gravity, and then you get 24 vector bosons for SU5. And then there's this matter sector right here where we get this, in terms of the SU5, it's known that you have the 10 representation and the 5 bar representation, as well as their complex conjugates. And then it's just very nice how the 10 has a 5 representation, whereas the 5 bar has a 10 representation. So there's just some cute little symmetry here. And when we break this SU32 into the conformal group, or one of the conformal charts out of the 3 conformal charts, then that would isolate one of the generations, and you would get some spinors here, or spinors of the conformal group as twistors, and then some scalar field here, some Higgs field. And then we'd also get some Higgs fields here with some fermions here. And so we're going to continue probably going into the super algebra aspect of this. So if we just focus on SU32 for a second, and we break it to SU22 with some U1, we get the spinors in the outside of this 3 grading with the 0 grade containing all of the bosons. And so when we take this quotient space, when we mod out by SU22 cross U1, we can think of SU22 cross U1 as the bosonic sector, and we get the fermionic sector, the odd part, as being these spinors. And we basically worked out through the representation theory, when you take the Grassmann envelope of E8 with respect to spin 12,4, and you look at the SU32 inside of it, you can determine that these spinor representations indeed turn out to be in the odd part of the superalgebra. So that gives us motivation to say that the Grassmann envelope of SU32 within itself is well defined as well. Or we could have just defined it straight there. But it's important to understand how it comes into E8 as well. And so we have this conformal algebra. Hopefully you guys have seen that before. And there's also this superconformal algebra, the n equals 1 superconformal algebra, d equals 3 plus 1. And so that adds these Q and S conformal supercharges. And they have these supercommutation relations. We don't need to go into details. And so when we get this gamma SU32, you get 3 charts of the superconformal group in d equals 3, 1, which is just fascinating and mind-blowing to me. This is a new mathematical finding. And so if you took one of the charts, let's just say you had this A generator, which corresponds to the U1 right here, you would get some matrix representation like this. And we know that SU22 has one, the compact real form would have, or the maximal compact subgroup, sorry, would have some SU2, which you could place as a 2x2 block here, and then I would have another SU2, which would be a 2x2 block here, and then the U1 would go here. But if we focus on SU32, we could say that there's this SU3 block here, or let's do it down here. There's this SU3 block down here, and there's 3 different SU2s we could pick out in that SU3. That gives us 3 natural charts of this superconformal group. And you might say, hey, maybe that's a little hacky, but the cool thing about this is that when you consider chiral spinors, even if you use these 3 different charts, when you include the projection operators, even if they're different with respect to the 3 charts, it's the same for the chiral spinors. It's always going to the first two components when you project onto that other SU2. So that it's suggestive that there's some good motivation for why you could use this to get 3 generations. There's a lot of, I mean, we're still going and exploring all the mathematical details. So perhaps this is evidence, but I think it's really solid evidence. And, you know, we have actions, we have Lagrangians and all that. So the evidence is pretty strong. So when we look at this Grassmann envelope of E8 and we mod out by SU5, I guess the point is that SU5 doesn't get affected by the Grassmann envelope, but SU32 does. So if we want to understand the supersymmetry here, we can mod out by SU5 because we know that that's going to be a bosonic sector. And when we do that, you get these super multiplets. All of the other representations, for instance, this 24,1 is corresponding to gamma SU32. Now, this contains a singlet of matter fermions with respect to SU5, which in the flipped SU5 model, so I'm actually going to focus on the flipped SU5 gut model. Usually in the SU5 gut model, the right-handed neutrino is the singlet, but in the flipped model, everything gets flipped, and so the right-handed electron becomes the singlet. And so this right-handed electron is actually in the Grassmann envelope of SU32, and it's combined with the conformal group. So there's this natural supermultiplet coming from this representation of SU32. And this other representation of SU32 gives another suggested supermultiplet where you get some matter fermions with some Higgs fields. And the 10 representation also has some matter fermions with some Higgs fields. And really, it's this focus on this 10 Higgs that is that's the motivation for why we ended up using flipped SU5 gut instead of the standard Georgi-Glashow model, is because when we use the 248 representation, we have to use this 10 Higgs. And so really the point of this slide is to just point out that this Grassmann envelope is showing us a natural way to get supermultiplets. But notice I didn't introduce any squarks or sleptons. There's no unobserved superpartners, right? Here, we have the right-handed electron and we have the conformal group. It's not introducing unobserved superpartners, but we have supersymmetry. So that's why I find this marvelous. I mean, it might turn out that the minimally supersymmetric standard model is a misnomer, right? How could that be minimally supersymmetric if there's supersymmetry here? All right, trying to go to the next slide. All right, so I'm going to talk about the gravitational sector for the next few slides. Obviously, we want to make contact with general relativity with this Einstein-Hilbert action, but it's not a gauge theory, and gauge theory is great for quantum field theory. And it's not too bad to really just gauge the Lorentz group and get Einstein-Cartan theory. It still has the Einstein-Hilbert action. It still gives you Einstein's field equations. It's basically GR. Loop quantum gravity uses this. String theory uses this. They don't like to talk about it, but they're using Einstein-Cartan theory. It's just that nobody ever wants to quantize Einstein-Cartan theory for some reason. But you can study it. And there's also Poincare gauge gravity. And it's fun to point out, if you gauge the Poincare group, that actually is gauging the translations. And if you gauge the translations, that's what metric teleparallelism is. And Einstein-Cartan theory is gauging Lorentz group. So this Poincare gauge gravity is actually not even a unique theory. There's tons of Poincare gauge gravity theories, but you can get it to unify metric teleparallelism with Einstein-Cartan theory. And then there's this metric affine gravity that contains curvature, torsion, and non-metricity, and that gauges AL4R, the affine linear group. But then there's also the conformal group as well, which contains the scale transformation found in the general linear group, but it contains these quadratic special conformal transformations, whereas the affine linear group is linear and doesn't have those quadratic special conformal transformations. And it's fun to point out that the infinite dimensional diffeomorphism group, which is foundational GR, is what unifies the metric affine gauge group with the conformal group. So if we really want to embrace the diffeomorphism group in Einstein's legacy, I think it motivates us to look into metric affine gravity and conformal gravity. So I'm going to focus more on conformal gravity for this talk, mainly because of the history. Sorry, if the noise, there's some background noise. If it gets too bad, I can tell people to be quiet, but hopefully it won't be too bad. And so we're going to synthesize a few different theories for you now. So there's this Yang's 1974 theory. There's Magdal-Mansouri gravity. And then there's this Kaku, Townsend, Van Nieuwen, who is in superconformal gravity. And we're going to gauge all of these groups. And I should probably get going. Basically, there's Yang-Mills theory. He gauged the general linear group, but it didn't really It included box equations as well. Maybe it's problematic, maybe not, but he used Yang-Mills theory for gravity. And there's this Gauss-Bonnet term, which is different than the Yang-Mills term, and you can get it from differential forms, and it's topological. But what McDowell and Mansouri did is they took the Gauss-Bonnet term, but they lifted the curvature by considering a higher gauge group. So they would take spin 4,1 or spin 3,2, and they would consider this, globally it's 4D, but locally it's 5 dimensions, and they would embed the frame field with the spin connection. And then they would find the lifted curvature from that, but then they would restrict the curvature just to the Lorentzian part. But you get this, since you contract some indices here, you get some 5D components coming into this Lorentzian curvature, and you get some frame fields. And when you put that into the action, I should also mention there was an error that they made as well. But basically, when you put that in, you can get Einstein-Hilbert plus the cosmological constant, plus the Gauss-Bonnet term right here. So the McDowell-Mansouri gravity theory ends up giving you Einstein-Hilbert plus the cosmological constant plus this boundary term. And something that isn't really pointed out in the literature that I computed is that if you do the same exact thing for Yang-Mills, it does work. And there's a lot of confusion in the literature. People aren't very clear about this. You would have to subtract away this term to get this, because this has some propagation and does some stuff you don't want. But this, you can get Einstein-Hilbert with the cosmological constant from Yang-Mills. So you can continue to the conformal group, and that's what Kaku et al. Did for their superconformal gravity. And they would basically gauge the conformal group or the superconformal group and then put it in this Gauss-Bonnet term. And the results from that were pretty curious. But another thing, they weren't able to get Einstein-Hilbert. So what's curious and something that I found is that when you use the conformal group for Yang-Mills and McDowell-Mansouri, it's almost the same, but it's slightly different. The coefficients are slightly different. So what I end up doing for this paper that we'll put out is if I take linear combinations of this, I can get the Ricci 2 tensor terms to cancel and leave this R squared term. And then just to get a quick way to get to Einstein-Hilbert, there was this paper from Gill and Sia where they realized that an R squared term, and there's also further history of F of R gravity leading to Einstein field equations, but there's this slick way. If you claim that you can introduce an auxiliary scalar field, then you can take this R squared term and replace it with this. It's a weird thing to do, but when you do this, you get this, and then you can basically get Einstein's field equations. And what happens is when you take the equations of motion for phi and you plug it back into the action, you end up getting the R squared. So in that sense, it's the same theory. You're just identifying some auxiliary scalar field. And that's very common in GR because the metric, actually, it should be the traceless metric. So there's a long history of scalar fields and general relativity. We're not going to add it as a propagating scalar like other researchers have done. We just use it as an auxiliary field. But basically, you can do this and get Einstein-Hilbert in that way. It's just a quick way to get Einstein-Hilbert from quadratic conformal gauge gravity. So we're going to move on to the flipped gut model, which typically was found because it fits nicely in the spin 10. And so it's worth pointing out that this U1 outside of SU5, they'll call it U1X. That's one U1, but there's another U1 because SU5 contains this U1Z. So typically the Georgi-Glashow model would take the weak hypercharge, the U1Y, and set it equal to this U1Z. But the flipped gut model identifies a different U1Y by mixing these two generators here. So that's the main difference there. All right, so if we write down these generators before we even pick which, if we're doing flipped or standard gut, you can write down these generators and you can isolate some Gelman matrices, some Pauli matrices, you can get some diagonal U1s, and you can have some fun with those generators. And then, so here, now we're going to introduce the flipped SU5 cross U1 gut spectrum. So the gauge symmetry, they'll call it flipped SU5, but they actually have to gauge SU5 cross U1. And so as I was mentioning, you get the charge conjugated electron in here as the singlet. You get this 5-bar representation to contain some U bars and the leptons. And then you finally get this 10 representation, which has all of the down quarks, some U, and the right-handed neutrino is in here as well. And so I use this funny index right here with the circle over it for the fundamental index of SU5. And so the flipped gut model requires a right-handed neutrino. And so E8, as I'm using it, requires a right-handed neutrino, which is very interesting considering the talk from Turok last week and the work of Latham Boyle, where they are finding utility of the right-handed neutrino. So that's encouraging. And I'm not even going to go into all the indices, but I just have a lot of fun with decorating indices in different ways. So I found out this scheme where I can build up to SO12-4 in this logical way and get to all these different subalgebras by adding different primes and bars and hats, but you can not worry about the details. So when we take these representations, we can break this down and then we get all of the fields. We can assign the fields. So here's a conformal spin connection. I use a bar over index for the conformal group. And so here's an additional gauge field. And then you can expand it further when you break the conformal group down to the Lorentz group. This would be the true spin connection. That would be the frame field. This would be the special conformal gauge field. Maybe there's some dilettante generator that has its gauge field. And then you can get some spinor fields here, and then the matter fields break away here. So this alpha bar is that conformal index, and then ij are anti-symmetrized for the 10 representation, where this hij is a Higgs, and then there's this little h as well. So the one unique thing about this model is out of all of the particles it introduces, it doesn't really introduce anything exotic except this new vector Higgs field. So it gives the flipped SU5 cross U1 spectrum conformal gravity, and it gives the minimal Higgs sector plus this additional vector-like Higgs field. And it's very curious because it also kind of looks like a frame field between space-time and SU5 in a weird way. So we still don't know the best way to interpret what even if this is the best theory to pursue or the best way to use that field, but we have written down at least one action using that. So just to summarize the gauge bosons, right? We have the spin connection that leads to the curvature. You could have the frame field that leads to torsion. We didn't consider propagating torsion yet, although I love torsion and non-metricity, but I just wanted to discuss minimal field theory. So that's kind of what Magdal-Mansouri did as well. They didn't consider propagating torsion, so I followed that. And you could also have this little a for the U1 X generator, which will have a little f mu as an abelian field strength. And then there will be the SU5, where I'm always using this little circle for the SU5 indices. So the capital A would be the adjoint index for SU5, and there'd be 24 gauge bosons there, leading to this field strength as a 2 form. And so let's try to get through this theory now. So here's the matter sector. As I was mentioning, you have this 10 representation, the 5 bar, and the 1 representation with spinners. And then we have this Higgs field, the 10 Higgs, the 5 bar Higgs, they're complex conjugates. And so this actually contains the electroweak Higgs, and then this is the new Higgs field. And since we have these 3 conformal charts, whenever you find the representations for one conformal chart, that's going to isolate one generation. But we can add an index for all 3 charts. And hopefully I can describe how to get the action for all this. So yeah, we can consider an action where we consider all these different contributions. And so this is the gauge theory sector. I already discussed the gravitational sector here. Basically, this is the Magdal-Mansouri, that's the Yang-Mills, and we take the linear combination such that that Ricci 2 tensor term cancels out. And then we're left with the R squared, and we do that auxiliary scalar field trick. And then we just simply add the Maxwell and Yang-Mills terms right here, as you always would do, nothing fancy here. And we have these these generators, we normalize them in the standard way. And okay, then we can add kinetic terms. Since we're in curved space-time, you just got to go in the literature and figure out how to deal with actions for spinors in curved space-time. It helps to kind of think of a dyadic operator that acts on both sides, so you can get the covariant derivative acting on both the spinor and the conjugate spinor. But for the most part, this is just your standard chiral spinor action in curved space-time, nothing too fancy. And then, just some scalar field terms here, right? Some Klein-Gordon terms there, nothing fancy. And then, so to understand 3 generations, I found this representation of CL44 by taking tensor products of CL11. And so it's nice because CL11 has these simple matrix representation 2x2 matrices, so that you can figure out some structure there and then get to these 16x16 matrices. And so this is really cool because spin 4,4 you can think of as if you took DS4 across S2, and you took the isometry groups of that, you get spin 4,1 with spin 3, which fits nicely into spin 4,4. And so this S2 is for mass flavor oscillations, and we get it with de Sitter. I think that is beautiful. And spin 3 has been pointed out as being useful for flavor symmetry. It was originally introduced in spin 18 gut. And now they're saying, well, maybe spin 18 is overkill, but we still can use the spin 3, but they don't have an origin. And we're saying the origin is gravitational, which makes sense because mass is kind of like a charge for gravity. And so this is actually very close to work of Wilson. Oh, sorry, I meant to put the archive number here. But we've been looking at quaternions in various different ways, but the way I ended up landing on it is that you can get complex structure from these Clifford algebras by going into the extra dimensions, even though you're using real Clifford algebras by considering an extra dimensional Clifford algebra. These are time-like rotations, right? We have that spin 3F that was outside de Sitter space. So we have these time-like rotations for mass flavor oscillations that help give us some complex structure. And so this is just the explicit realization of those generators, those rotation matrices, and you can confirm that they give you a representation of the quaternions, even though they're just they're real 16 by 16 matrices. Everything's real, but algebraically it's quaternionic. So basically you can form projection operators. You can look into the paper for the details, but you can get chiroprojector operators for the 3 different generations. And you can also project out the mirror fermions, because as soon as you focus on one conformal chart, you're going to get normal matter and mirror matter. So naively, you would think you wouldn't get 3 generations. You would just get 1 generation with mirror fermions, which is no bueno. But if you're going to use this mechanism to get 3 generations, you're going to have to project out the mirror matter as well. So you can combine these projection operators together. And what we're able to do, you can look in the paper that's on archive, is we were able to show how to get an action that used these projection operators. And a big part of it is to figure out how to implement the complex conjugation, because you have this psi bar spinner and you're going to need the gamma 0 and you needed this star. And so we found that instead of, we can use a matrix to implement the complex conjugation. And so we can include that in the action to encode that complex structure. All right, so this is so you can schematically write it out. Once you have these projection operators, you can identify 3 different generations, even though we're using a 16 spinner. As soon as you apply a projection operator, you can get an 8 spinner, and you can have 3 different projection operators to give you what appears to be 64 different degrees of freedom, but they're actually projecting all from a single 16 spinner. And so these 3 terms are equivalent to these operators. There's a sum over 3 different types of operators here acting on a single 16 spinner that gives us 3 generations. And so that's that. And so that you can do the same thing and uplift it to the standard model to get the 128 spinner in E8. That was just doing it for the 16 spinner for 1 particle. And then you could extend that to the entire standard model. I'm just going to try to finish up, hopefully maybe take another 10 minutes here. I think I've lost a lot of time just from trying to go to the next slide. It's a little slow. Yeah. There we go.
10 minutes, okay. 10 minutes, good.
Definitely, thank you. So we can take covariant derivatives of these matter fields, and these are going to give you things like the spin connection and the different gauge fields, and the different charges coming from the representation theory figures out what fields should be included. If you have a singlet with respect to some group, it's not going to interact. It's going to be trivial. But then if you have some U1 charge, for those might come in here. So really, the representation theory is giving you almost the whole theory. I mean, nothing I did for the Lagrangians besides the 3 generation trick. That was maybe a little new, but you know, it's not too hard to just write down all the possible potential terms for this Higgs sector. You just consider what are all the renormalizable terms, and you get this this nice spectrum here. And it's curious because this 10 Higgs has been used mainly in supersymmetric flipped gut. People haven't really studied it as much with the non-supersymmetric flipped gut because the SUSY researchers were the ones who introduced it, and they found so much utility out of it, yet it has all of these squarks and sleptons and superpartners. So at this point, I would say their Higgs sector, their potential term is better. I need to do a lot more exploration. There's a lot more work. I'm not claiming that these potential terms are what nature is actually using, but it's something that you can write down. It's a concrete model, and we can explore and see what the properties are. Does it have proton decay? What are the masses that get derived. I've looked into a lot of this, and it's kind of what you would expect from a grand unified theory at this point. We're not introducing any crazy mechanisms to try to fine-tune things at this point. So, I mean, proton decay is a problem for all these gut models. So we're not really solving that problem. But this 10 Higgs has found a lot of value in the flipped SUSY gut model. So we were also able to get one more term that they had. I just mentioned there. And so that's kind of the conclusion of this theory. So that's kind of, I still have more backup slides if we want to have more discussion, but this is kind of a good stopping point for questions, and I could stop here if we want.
Yeah, so thank you, David. That's a very fascinating coverage of E8, a great deal to learn. So maybe we could have a discussion, and if some time still remains, you could come back and take your further slides. Does that sound okay?
Definitely, that sounds perfect.
Great. So thanks again. Thanks so much, and for building on to this excitement for E8, which we are seeing for the last 2 years or so. So please go ahead with your questions. Yeah, Bernd, please go ahead.
So maybe it's just my misunderstanding, but you talked about an octonionic Jordan algebra. I don't think this works because...
Oh, yeah, no, totally. Yeah, maybe I was too quick. No. So there is no octonionic Jordan algebra. You have the octonionic Jordan algebra. However, when you're interested in E8, and specifically the Freudenthal-Tits construction, what it does is the construction uses a tensor product of alternative algebras with a Jordan algebra.
With the exceptional, yeah.
And so it's pretty general. It doesn't have to be the exceptional Jordan algebra, but specifically obviously when you choose it to be the exceptional Jordan algebra, and you choose that other alternative algebra outside the Jordan algebra, when you choose that to be the octonions, you get the tensor product of the octonions with the exceptional Jordan algebra as having applications to E8.
Okay. Thank you. Then Mr. Drake can continue.
Yeah, Tavian, please go ahead.
So, David, first of all, thank you very much for perhaps too much information content too quickly, but otherwise very nice. Could you go back very early? You said something about the history of SL. No, you don't need to show the slide. That's too hard.
Okay.
SL3R versus SU3 for QCD, and what people knew about that and why it matters.
Yeah, so honestly, I haven't exhaustively read the papers. I've skimmed them briefly. Essentially, a lot of people are concerned with non-compact gauge groups because you have to get infinite dimensional unitary representations. I'm not sure if it was for exploring like higher multiple. I don't exactly understand the application. It's worth looking into more. I just figured I would share these works because it has been discussed. But yeah, so it's worthwhile to point out. I mean, they were thinking about ST3 and SL3R, but I also would point out that I'm not saying you can't use SL3R for physics. I do think there was too much hesitation with this whole infinite dimensional representation thing. For instance, there is some work, I forget the name of the author. I forget if it was Cahill or someone else. There is some work in the 1980s discussing how to use non-compact gauge groups for gauge theories, which is underappreciated. So I'm not saying you can't explore physics with this, but people have thought about this, and I think it's worth exploring more this notion of non-compact groups. So,
well, let me just say that I agree that I've heard many people express these concerns based on history, but I don't yet understand what those concerns actually are.
Yeah, I mean, essentially the idea is that you don't want to use infinite dimensional representation for the fields, roughly speaking. But actually, if you look into Weinberg, he seems to clearly articulate that you don't need unitary representations for everything. Like there's kind of the difference between, how does it work? I don't know, there's like the field and then the operators. There's some subtle things where if you read Weinberg very carefully, I'm not sure if it's actually a problem, but I don't know. Yeah.
Okay, thank you. That's kind of the answer I was hoping for, and I appreciate the clarification.
Definitely.
More questions, please.
Yeah, let's see. I didn't have a chance to look at the chat. I'm not sure if there was.
Yeah, there's a lot of vigorous chat today. We are going sort of in parallel when you were talking. The discussion related to your comments. So you could see that. Bernd, go ahead, please.
I have a follow-up question. You mentioned that you work in some models with 3 extra time dimensions. Is it correct?
Yeah. Yeah.
3 additional time dimensions. Normally, if you introduce more than 1 time dimension, this causes a lot of trouble with ghost states and tachyons and many unpleasant
All right.
stuff.
All right. So yeah, I worked through this extensively. The original paper, there's a version I probably not even on archive where first Itzhak bars show how to remove ghosts for 2 times.
Yeah.
First of all, I generalized that to arbitrary time dimensions. So what he did works for arbitrary time dimensions. I didn't publish that result, but regardless, it doesn't
Please
matter.
do. I mean, this is really.
It's a distraction because it's a distraction because no one reads bars work anyway. So it's a distraction. The point is that all of these theories that I'm just constructing are still 4-dimensional. I'm just using representations from some higher dimensional algebras that happen to relate to extra dimensions. So another way to say it is that maybe if you're pursuing a unified field theory, you have some manifold for space-time, and then you have some gauge group, and they're 2 separate structures. And your fields are going to have to come into representations. Typically, the matter sector you're going to want to create as all in terms of the gauge group representations. And so you could have the manifold be 3 + 1 dimensional, and it would have no ghosts, no tachyons. But you could still gauge a higher symmetry that just happens to have extra time dimensions.
Okay. So
and that's not even what I'm doing either. I'm not even gauging all of E8. I'm just using the representations that happen to relate to the extra time dimensions. And so in future work, I am interested in exploring. Actually, if you really go into math, I think string theory is kind of going in the wrong direction. I think maybe there's more time dimensions than space dimensions. Maybe it's I think what they have with their 9 + 1 is really more like 9 time dimensions in 1 space, and they should add an additional 3 + 3 to that to get to the 12-4. That's just the way I look at it. But yeah, so you could explore in the future more sophisticated models that are string inspired, that attempt to actually take extra time dimensions seriously, and then maybe look into bars work, and then try to consider compactification. Maybe there's some membrane dynamics that could figure this out. But you don't need to do all that. You can just consider a conventional D = 3 + 1 theory without any ghosts and use these algebras. So that's why I focused on that for this talk, because I don't want to get into all those complications. I want to first understand the minimal possible thing. Like if we don't need to go to D = 9 + 1, let's just stay in D = 3 + 1 to start.
I see. Okay, thank you.
Yeah, Bernd, maybe I could react a little bit to this point about 3 time dimensions. What I'm seeing in my work with E8 cross E8 is that I get our 4-dimensional space-time. Let's say 1 time-like direction, 3 space-like directions. Let's say plus, minus, minus, minus. Then I get another quote-unquote space-time, which has 3 time-like and 1 space-like directions. So if you have plus, minus, 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 that is minus plus, no, if you have plus, minus, 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 that is plus, 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 minus.
Okay,
and
so
we have an intersection of 1 time and 1 space direction, so that effectively all put together we have 3 space-like and 3 time-like directions. I at the moment don't know what to make of this other space which has 3 time-like and 1 space direction. It looks very real in the sense that the theory demands it. If the other things are to be gotten, like the standard model and gravity, I can't do away with this, but I don't know what physics is hiding. It's very interesting.
I'm suggesting that it has applications to mass flavor oscillations.
Yes. You're in this context, 3-3, yeah?
Yeah.
Yes, I think that's a very good point. Yes. Okay. So flavor eigenstates in 1/2, flavor eigenstates in 1/2, mass eigenstates in the other half. That's what you're saying, no?
Probably not exactly. I suppose what I'm saying is that if you took a spinner in d equals 4 plus 4 and you went to the Lorentz group for space-time and you looked at the spinners that you get out, there's tricks that you can do to get 3 generations in only a 16 spinner when you naively would think that you need 24 off-shell degrees of freedom. And so that's a big problem with E8. If you wanted to use the 128 spinner, one of the big problems was you need 192 off-shell degrees of freedom for the standard model, which doesn't fit in E8. So how do you make that work? And the extra time dimensions are what makes it work.
Yeah, so it probably is telling us something which has an application. That's what you're saying. Yeah, I see a connection with how I have been looking at neutrino oscillations. Yes, that's a very good point. Yes.
I would like to add a small historical remark. There were ideas in the 60s and 70s on an extended relativity where they used the space-time with 3 space and 3 time dimensions, then a generalization of the Lorentz group acting on the space-time to allow for superluminal particles. This was an idea which was pursued by Recami, an Italian researcher. So maybe there's some link, or maybe there's no link. I just wanted to mention that there are older works.
Yeah, so we actually have, there's been some recent work as well talking about tachyons. Yeah, there's a lot of other things that I've been working on that I didn't mention. There's a possibility there that you could argue, how did that end up working? Yeah, there's another way to look at phase space and start thinking about that and look at Born reciprocity and start thinking about tachyons. Because I mean, really string theory, the point of it is it's supposed to be relevant like above the Planck scale. And that gets into T-duality, which relates to Born's reciprocity, which ends up getting tied up in tachyons. And there was, independent of string theory, there was also a recent paper that I'm trying to remember. They used, maybe they called it time space or something, but they used something like this for tachyons. And so, yeah, there's some stuff that could be found there as well. It depends on what type of model you're going after. I mean, do you believe tachyons are real in the first place? You know, well, also, are they even faster than light? I mean, they could actually be slower than light. Depends how you interpret the mathematics. So,
True,
yeah, there's lots of, yeah, another point I'd like to articulate is a lot of people seem to have this idea that we just find the right mathematics and then it'll give us this unique physics theory. And my work is suggesting that is absolutely not true. There's the mathematics, and oftentimes there's many different ways you can apply that mathematics to different models. And so that really does need to be taken into account.
Yeah, this is true. So, and I would be careful when working with tachyons.
Bernd, one more remark, Bernd, since you brought it up, and that is the attractive possibility of using this extra, these time dimensions for EPR. I mean, I'm looking into it. A quantum entangled state goes through this whole lot, not just our 4D space-time, but through these extras also. And one can argue that distances in this other quote-unquote space-time are much smaller, and light or a signal going through them arrives at the final location much faster. It is not superluminal. It is at the speed of light, but it is traveling a shorter distance. And that is why it arrives at Bob, let's say, from Alice, faster than it can go through our space-time. And then it looks like quantum non-locality. Quantum theory is local, but there are additional dimensions through which one can go. I mean,
they have a shortcut, so to speak. You have an extra dimensional shortcut.
Yeah. Well, some people might call it a wormhole, but now we are not sort of mixing GR and quantum theory. We are just actually seeing the additional dimensions, which are shorter. And
for distances and the additional dimensions are smaller than in our space-time.
Yes. This can be actually argued. This one can make a case for that. Yes.
Okay.
Yeah, and if I may, the analogy to wormholes or black holes is very appropriate because I believe it was at Brown University. I saw a team, maybe UMass Dartmouth, but there was a team working with simulations of black holes, and by their models, when you're computing black hole mergers, You need the volume inside the event horizon to have three time-like and one space-like dimensions for some reason, or that's
Okay,
for the
can you say
purposes of
that
their
again?
calculations.
Yeah. Because in some sense, that's one idea I also had. When you are inside the black hole, when we say that space and time interchange roles, something like that is happening, right? That's what you're saying.
Yeah, and then it made their simulations self-consistent or easier or something. I forget the details, but I could definitely
Yeah.
look it up and get it to you.
Great, thank you. Yeah. Thanks for bringing this up. Yes, it seems to tie up what's the inside of a black hole.
Michael, do you mind trying to send me that paper? You said there's a paper mentioning this.
I believe they produced some papers. I need to look up. I was quite young then, and my father was visiting the university there, and I just saw the supercomputer they built out of. So he was like working at IBM. He invented some, or he led the project to develop the cell processor, I think, and then so they were using cell processors to make a supercomputer, and he was going to help them with some software, hardware stuff. So
Was this long ago?
yeah, this was easily a decade ago.
Okay.
Yeah, but I'll go ask my dad where that was and see if I can dig up the papers.
Yeah,
And
thank you.
a follow-up question, so because you said there was a connection to wormholes. I once read a paper where they also used wormhole topologies and geometries to model merging black holes. So maybe this is the same or something similar. Is this related? Hello?
I'm not sure. I was quite young at the time. I was a high
Okay.
schooler. I was like a high schooler,
Okay.
basically.
So I see.
Yeah.
Okay.
Also, David, since you have studied E8 so extensively, where do you see this going? I mean, we don't want to spend all our lives just searching E8 here and there. We want to find this, what you call light at the end of the tunnel. Next few years, you
Yeah.
pointed out, of course,
Yeah,
the
definitely.
work
I mean,
of Tavian, Corinne, and Rob. And where do we see this going from here?
well, I mean, I think what's been opened up is that there's really, I guess I suggested that there's 2 or 3 really good directions for gut models that can be explored with gravity. I mean, so exploring all the phenomenological implications will take a lot of work, but it's the perfect amount of work, right? What I'm saying is that there's 3 paths to the conformal group with U1 cross SU5. And you can go through SE72, you can go through SE32 cross SE5, or you can come from spin 12,4, or you could also explore E8, and maybe there's a couple models there, and then just really diving into the phenomenological implications, and also a more extensive view of the differential geometry, and looking into spontaneous symmetry breaking on the gravitational side of things more rigorously is required next, because the work I did here was building up from Kaku and the superconformal gravity work, but there's actually some later work that shows how to spontaneously break the superconformal group, and it's pretty complicated stuff, but someone needs to dive in there and figure out what's going on there. And basically the conformal group has some non-metricity in it, and so there's no notion of supermetric affine gravity right now. So I have some notes on that, but I mean, so basically this whole story is suggesting that there's a way to use supersymmetry in a way that's different than what all the string theorists are suggesting. And so I think figuring that out is worthwhile. And yeah, I'm also not saying E8 is the theory of everything either, because we actually have some work suggesting that going beyond d equals 11 plus 3 to something like d equals 27 plus 3. I mean, it might make sense for describing dark matter. I'm not going to claim that this is the best theory of dark matter out there, but there was some dark matter researcher who came to us and said that she had some analysis suggesting that 2000 degrees of freedom would work nicely for galaxy generation in this warm dark matter. Most people think dark matter is cold. people looked into hot dark matter. It doesn't seem really likely. She basically identified there's this narrow sliver that people don't look into in this warm dark matter regime. And so she ran with that and thought that there should be 2,000 degrees of freedom based on some analysis she had. And it just turned out that this 2048 spinor representation came out of all these superalgebras and just naturally fit in with our understanding of E8, yet gave us something beyond E8. And so, and it's also related to the Leech lattice and the monster group to some degree. And so it's mathematically very rich. And, I think it'll just take a lot of time experimentally to figure out, we don't even know if grand unified theory is the right idea. So if that's the wrong idea, then, maybe all this work is a waste of time. But it's hard to believe that the standard model is like the final answer to everything. So yeah. I think hopefully there's a lot of possibility for work to be explored now, especially we have a lot more octonionic mathematics now. And hopefully this is it's kind of been taboo, right? It's very difficult to even get it published, right? So hopefully we can just keep pushing forward and start to change the perception a little bit and get more of the community involved.
Yes, thank you. You know what? One thing that makes me uncomfortable is first having guts and then trying to add gravity onto it. I'm much more comfortable with thinking of weak force, having an analog with general relativity and trying to bring them together and then add on, QCD. And I think your 60 paper is in that direction, 60 spinners trying to look at the relativity.
I would argue that perspective of like grab a weak unification, in my opinion, if you were to put a gun in my head right now, I think that has nothing to do with gauge symmetry. I think what's actually going on, what's really interesting about all of this is it's not just about exploring one chain of subalgebras. To really figure this out in that paper, we had to look through multiple chains and put it all together. And so what I think is interesting is this idea is that maybe there is some extra dimensional theory that eventually leads to a 3+1 theory. And when you do that, I think what the string theorists have been overlooking is this idea is that the global manifold structure is different than the local gauge group structure. So maybe the spin 4, and the octonions is related to the global structure that is somehow dual to the gauge theoretic structure. And that paper, what it was showing is that you can start from E8 and go down different chains and lead to the same spot at low energy. And your whole thing is kind of trying to embrace this low energy unification idea. Whereas I'm more interested in still making contact with the conventional gut models, which makes it harder to connect to the octonions. But I think what it's actually suggesting is that the octonions are showing some exotic global structure, some hidden dualities inside some larger theory that we haven't really figured out yet. And so that's what I think, that's what I would recommend is that's at least what I'm seeing.
Great, thank you. So we have a question from Rob. Please go ahead.
Hopefully you can be unmuted.
Yeah, I'm sorry. Yeah, no, you're there now. You're there.
I'm sorry. I was going to ask a question about 10 minutes ago, and I've lost all this stuff about bigger and bigger and bigger theories. Just gets me going, because we need a smaller theory, not a bigger theory. So
I agree.
Come and listen to my talk in November, and I'll explain how it works with a very small theory.
Yeah, maybe you could add some more already, Rob, and
Sorry?
give us a glimpse of what is coming when you say small. I'm very interested in your remarks. Are you thinking in terms of Clifford algebras?
What I'm saying is we need to understand the finite symmetries, understand the 3 generations of fermions, understand why there are 4 types of particles, neutrinos, electrons, up and down quarks. And when we understand that, everything else will follow. That's what I believe.
And It's the forces, the gates, you'd have 4 forces only or more?
Well, in my model, I have 4. I have
Okay.
I have no more particles than exist already, no more forces than exist already. It's
And
all-
dark matter, dark matter?
There is no dark matter. Dark matter is a, well, in my opinion, it's a it's to do with having the right coordinates for your space-time.
And no sterile neutrinos also?
I haven't identified all the particles, so there may be a sterile neutrino, but I don't think so.
Mhm. Okay, great. Yeah,
Anyway,
certainly looking forward to your talk, very definitely. And what's the, okay, yes. Any more comments, Rob? Okay, so
Yeah, I agree that the discrete symmetry is definitely interesting to look at. He's put out a lot of interesting papers recently thinking about discrete structure more seriously. And you could write down simpler theories. You know, for instance, I could just write down a theory that uses a subset of the representations in E8, but this was just to demonstrate where E8 goes. I'm not saying that E8 is the right theory. I'm just trying to show what E8 could give you. And so, yeah, I mean, it's probably not the right, what I've presented today is not the right theory, which is good because it gives us more work to do.
Mhm. Yes, yes, yes. So, what is your take, David, on string theory, string theorists, and octonions? I mean, did they treat them well? They were with E8 cross E8, but how much of this they related to octonions?
It's very related. And I mean, essentially the problem is that they couldn't figure out the octonionic math in the 70s. And so the pioneers of string theory knew that the octonions were related, but they couldn't publish any results on it. So they didn't not.
Okay, so that's very good. So what I would like to ask you is, what are you highlighting as the octonionic math of physics that we have learned, which string theorists did not know, and which, if they had known, would they have actually succeeded to unification?
Well, I mean, so there's the octonionic math, and then there's the physics. So, I mean, some of them do know the octonion math. I mean, Michael Duff is an expert in that. Mia Hughes did some great work with some of those collaborators, and they really mapped out everything. The division algebras classify all of the supergravity theories, right? But I mean, supergravity has a gravitino, and it's like, is that real? I don't know. I personally don't really like the idea of assuming that there's a gravitino. I think the unconventional supersymmetry from Zanelli and Alvarez is a very sensible idea, because really the the graviton, the spin 2 particle, it has this spin 3/2 super partner. But when you start to look into what supergravity is, it's a gauge theory. And newsflash, that global metric is not a gauge field. So really, you have to factorize the metric into a frame field. And the unconventional supersymmetry factorizes the gravitino into a spin 1/2 field with the frame field. So I really like that idea. I think I even had some slides where I used that for this crazy. I actually was playing with gauging E8 minus 24, and I used that unconventional just to show an example. I don't know if I can find it. So the octonionic mathematics might help with cleaning up some of the calculations, but that could also be debated because it's very difficult to make. Yeah, like I can envision the octonions leading to a nice spinor helicity formalism, 4D equals 9 plus 1, but then you have a lot of work to do to catch up with reproducing all the results they've already made. So that's a challenge.
Yeah. Yeah,
And
one
so,
point I would like to add, which you could tell me if you agree, that, even when working with octonions in E8 cross E8, string theorists would still think of, say, fermionic states as being made using complex numbers. But what we learned from Cole's work is that, let's say for one generation, you take octonions, you make a CL6 algebra, you make spinors from them. And now it's very fundamental that your fermionic states are made from complex octonions. That's very, very important. And to me, that is one thing which the string theorists missed completely.
I
Would
personally
you
don't think it really matters. I mean, a spinor is a spinor. If you represent it with octonions, if you represent it with Clifford algebras, if you use matrices, to me, it really doesn't matter whatsoever. I mean, the spinor is the spinor. As long as you can get the math to work and you get the right answer, that's all that matters to me.
Okay, so I'll tell you where I disagree. Again, show me if I'm wrong. The exceptional Jordan algebra, as far as I can tell, has to do with the octonions. And at least for me, J38 is very important. If I want to say, get coupling constants out, I will never get standard model coupling constants out if I work only with complex numbers. So, I mean, I would like to know your take on this. The J38 is octonions, right? You can do J38 with complex numbers. You agree, no?
Well, I mean, I'm mainly interested in understanding renormalization of coupling constants personally. So
I need their limiting values. And someday I need what the asymptotic values are. They are fundamental.
I mean, to me, they're not. To me, they're not fundamental. To me, the Baire charges, the Baire coupling constants are fundamental to me. That's just when I think about quantum field theory.
Some numbers. You need some number. Where do I start getting numbers? The CK matrix, parameters, Newton oscillation.
After we renormalize, I would think.
Yeah, no, but what is my starting point?
Your starting point is the Baire vacuum. And the thing is that nobody's done that because they think that QED is not UV complete. But you need torsion to make it UV complete, as shown by Pavlovsky, and nobody wants to study it. So the problem is gravity actually solves infinity problems in QFT, and no one wants to study it.
Yeah, but somehow my picture is that the Baire vacuum is a baggage we are carrying from quantum field theory. We can speak a different language in which I will get the asymptotic coupling constants, and then I will run them the way QFT runs them, because
we can ask the simple question.
Your philosophy, I think your philosophy is coupling constants run down from higher energies, maybe. Mine is the other way around, the limiting free values are fixed by the exceptional Jordan algebra, and then I will have them run to higher renormalized values. And so I think complex numbers versus octonions makes a very fundamental difference to my understanding. Otherwise, am I doing just group theory with the E8? What does it tell me with how to describe space-time? I'm saying space-time is described by octonions and quaternions fundamentally. It is not described by real numbers. Describing space-time by real numbers is an approximation which makes us lose a lot of information. We can disagree, but I'm sharing my
Well, I personally think that the split octonions are very helpful for space-time in my view.
Oh, yes, I agree. Yeah, Rob, please go ahead.
You said that you think these coupling constants and mixing angles and things are not fundamental.
Rob did say that, not me.
I entirely agree. And I have been saying this for 10 years, and people get so angry with me when I say this. But it is obvious, because all the experiments prove it beyond a shadow of doubt. You just have to look at the experimental results, and it's there. You can see it.
Which way are you, Rob? They are not fundamental.
They're not fundamental. Of course,
yeah,
they're not fundamental.
We could say that.
They can't be fundamental.
When you see a number like 1 by 137, or why is the muon 200 times heavier than the electron? Where is the proof? How will I do it?
It's summing over all of the quantum vacuum fluctuations, which is obviously.
Okay, but that's okay.
Exactly.
Get me the number 206 out. Do whatever
Look at the
you like.
vacuum over the.
Yeah, just
over
look.
the
All right, here's
solar
just think about this.
Integrate the
How much
vacuum over the
energy
solar system.
does it
And
take the
you'll see
universe
it.
to create an electron? Just think about this. How much energy does it take the universe to create an electron? Just think about that and go into QED, and you'll see why nobody is doing this.
I'm
It's
saying
because
you
we
could-
currently think the universe requires an infinite amount of energy, and
Okay.
that problem has been solved by Poplavsky using space-time torsion and Einstein-Cartan theory, and the result is so great that when you tell other people about it, they don't even believe it. It's too good to be true because they're used to it not working for 50 years.
Yes.
At the end of the
And
day,
they
you
can't even see
should
it
tell me-
working. They refuse to even think about what makes sense, which is that you have the Baire charges shouldn't be infinite. They should be finite. Paul Dirac pointed this out.
I don't want to put theory before experiment. At the end of the day, the muon is 206 times heavier than the electron. Please prove that for me.
Right. I mean, I'm just saying the calculation is very difficult.
Yeah,
I mean-
I give you a simpler way. I proved it just from J38. You should then tell me what I'm doing. Why is it wrong?
You should tell me why that proof is valid.
Okay, it's okay. It's Rob, anything more?
Well, I find it hard to explain why the muon is 207 times heavier than the electron, but I can explain why the proton is 1,836.15 times heavier than the electron.
Yeah, that's good, but a proton is a composite. First, I will want to know the quark masses, how they relate to each other. Why is the
Why?
down
Why do you
9
want to know about the quarks first? Why don't you want to
Because
know
they are
about the
more
protons
fundamental.
first? And,
No,
sorry, I'm going to mute myself.
No. Okay. Thank you. Bernd, please go ahead.
It's a pity that Mr. Wilson muted himself because I wanted to ask him a question. So,
Rob can hear you. Rob can hear you.
okay, so what is your view on coupling constant? Do you consider them to be something like material constants in the material? The material in this case would be the quantum vacuum. So they're not fundamental at all. They're just the kind of, properties of the quantum vacuum, just like material constant in some crystal are derived from the physics of the crystal and are not fundamental. Is this your view?
Yes.
You're asking Rob?
Yes.
Oh,
Rob,
okay.
kindly, if you can, please answer Bernd.
He answered me.
He said yes.
answered.
Yeah, and I have a similar view as well.
He briefly agreed. He just said yes. It was a very brief and precise answer.
Okay.
I mean,
What worries me is I don't want to put QFT before data. The data is telling me what's the muon to electron mass ratio. The data doesn't know about vacuum and renormalization. I just have a mass measuring machine. It churns out these two numbers, and I'm puzzled. Where is this ratio coming from? You're welcome to use your theory as you like. But please don't say it's very difficult. You have to solve the problem.
No. I mean, I'm just saying that we don't understand quantum field theory well. We do not understand non-perturbative Yang-Mills theory. We're not going to figure this out until we solve that problem, and it's obvious we're far away from solving that problem. I mean, maybe we can get some argument that gives us the mass value. I'm just saying that me personally, I'm not interested. Like, I'm only interested in deriving masses if I can understand all the whole renormalization. I mean, unless we're just going to throw away the quantum field theory altogether, which I'm totally down to do. I have some slides on that as well.
Quantum field theory and space-time is emergent from Adler's trace dynamics. And when we do things with trace dynamics, somehow they look more nice like classical dynamics with matrices in the true spirit of the Heisenberg quantum mechanics approach. Heisenberg was doing matrix dynamics, but he had the Heisenberg algebra. Trace dynamics is Heisenberg dynamics without the Heisenberg algebra. It's classical dynamics of matrices. Then I never have to talk of the bare vacuum and how I need to dress up.
I mean, if you never talk about that, then you're not doing quantum electrodynamics. I mean, I don't
it
like.
Emerges. Quantum electrodynamics emerges. It emerges.
Does renormalization emerge? I mean, eventually it's going to have to come in the story, or it's not.
Yes, it emerges. It must emerge. It must emerge. That I agree. I totally agree. But
And
if
so,
there,
do you
if
get
there
a
is
finite bare charge or not? I mean, that's the main problem. Let me just try to summarize the problem here. People thought that the bare charges were infinite, and that makes no sense. And people couldn't figure out how to make them finite. And that's why no one has ever been thinking about QFT in a sensible way ever since. But if we know now that torsion can help make those bare constants finite, I mean, we have to think about, if we're going to use quantum field theory or claim that we're going to get quantum field theory to emerge, we need to see what that means. I mean, we can't just use it and then ignore aspects of it. And so, I mean, eventually the renormalization will come into play. I mean, the interactions of the vacuum dress the particles and redefine the notion of what the particle is. So, I mean, I guess what I'm saying is if your theory is predicting how QED is going to emerge, along that story, you're going to connect to the bare couplings before the renormalized.
Yeah, I think my understanding is that when QED emerges, you already have a space-time continuum. And then I'm probably stuck with the infinite bare charge. If I want to go away from that language, I must go away from it in totality. I want to do trace dynamics without a space-time continuum. That's where discrete structures like octonions come in. And in that language, I thought one can talk of finite mass ratios and use those asymptotic values in emergent QFT, and then let them run. But to my understanding, you would still have an infinite bare charge so long as you are on a space-time continuum.
I mean, that's an unphysical theory to me. I mean, to claim that the universe...
It is. But the only way for me to make it physical is to go away from the space-time continuum. And then, to my understanding, we must go away from QFT also. And at least for me, trace dynamics is a good bet if I want to work without space-time. Bernd, please go ahead. Thank you. Thank you, David. Thank you for the discussion.
I just want to add a little bit on the torsional regularization of quantum field theory. Maybe David can also correct me, but if I got it correctly from the papers of Problavsky, what he's doing is he introduces a changed momentum space. So the momentum operators don't commute among themselves, and the commutator of the momentum apparatus is proportional to the torsion. And what he also does, the spectrum of this non-commutative momentum apparatus is discrete instead of continuous, and so he replaces the integral over all of the continuous modes of the field by a very large sum over discrete eigenvalues, and this is what makes his theory finite. And then he can calculate finite renormalization constant and can calculate it doesn't matter from which direction you go. Either you go from the dressed value and calculate the bare value, or you can also start from the bare value and then calculate the dressed value.
But you get a finite bare. That's the key.
Finite, that's important. The bare values are finite because he uses non-commutative momentum operators with a discrete spectrum, and thereby he gets rid of the infinities, and he can calculate a finite bar charge and a finite renormalization constant and coupling, which then also explains the bar charges.
And this is done because of gravity.
Yes. Because because
gravity is
the torsion vanishes,
infinity
the
problems,
commutators of the
not making
momentum apparatus would vanish also if the torsion vanishes. This is what's important here. Yeah. But Mr. Wappel wants to add or say something.
Yeah, Rob, go ahead, please.
Yeah, it's gravity. You have to deal with gravity. If you refuse to deal with gravity, you can't do anything.
That I agree. Yes.
What else is there to say?
And before you quantize gravity, you have to understand classical gravity.
Yes. And general relativity.
Yeah, I mean, I'm with Penrose on this. We never quantize gravity. We have a pre-spacetime, pre-quantum theory from which gravitation, classical gravitation, and quantum field theory are both emergent, essentially at par, I would say. So, because writing down the rules of quantum theory pre-assumes the existence of a classical spacetime. So I don't want to apply those rules to classical spacetime. Both have to emerge. Classical gravitation has to emerge first, and then quantum field theory has to emerge. And there is something underlying from which these two things should emerge.
Well,
perhaps.
More questions, please. More questions. Michael, how are you doing?
Sorry, I'm just unmuting. We're doing fine on time. Just if people just want to keep going, it's been an utterly fascinating discussion, and
Great, yeah.
Yeah.
it's been an exceptionally rich and vigorous
Definitely.
discussion. Yeah, I mean, there are at least 5 things I would like to comment on, but I don't think it would be appropriate. I'm going to try and formulate some questions and send them, perhaps post them later in the chat.
Yeah, great. Yeah, I'm trying to read your slide, David. Yes. So, next, please go ahead. Please go ahead.
Oh, sorry, me?
Yes.
Yeah, if you have
yeah.
questions, please go ahead.
Are there more questions?
Yeah, so next talk we have Corinne Minogue, another very interesting E8 talk coming up. The title is E8 and the Standard Model. So I think it's going to be very interesting once again. That is 2 weeks from now, Friday, 2 weeks from now, I forget. It's around 15th October, I think. So anyway, I'll send you a reminder.
Sure. I may have to ask Adrian to set up the connection on that, because I shall actually be away that weekend. But I'll know more certain. I'll be more certain of that in a few days. But don't worry, it's ring fenced in the diary for.
Yeah.
This
So
was the transcript of this discussion. I think will make for very, very interesting reading, and will deserve very careful reading.
Do these get preserved, Michael? The chats get preserved?
Yes. Oh yes, of course. What you're seeing, of course, I was forgetting. What you're seeing on the YouTube channel is just the video, but the transcript of the chat is preserved in the original in the original Zoom recording. So we have all of those. No, we have transcripts of all of the recordings. There's probably a way of sharing those. We could perhaps put them in a we could put that online and just make a site where people could click on and read those. I don't think it can be done via YouTube, but certainly we could make them available.
Yeah, thank you. So there's a nice comment by Corinne who says, I'll be playing much the same game as David with some different choices. So thank you, David, for setting things up so beautifully for me. Great. So I hope in the coming years we will converge on E8, and instead of that, we have a lot of riches. We have to pick something up and say, yes, this is it.
Definitely. And one thing I just thought of that I probably didn't articulate is that this Grassmann envelope of E8 minus 24 is the D equals 11 plus 3 superconformal algebra, which is very interesting for potentially course correcting string theory. So I figured I'd just mention that as kind of a final point.
That's 3 time directions.
You could have discussions on whether it's 3 time or 11 time.
Yes. Okay. Yeah, I see what you're saying. Yes.
I was very
But if you wanted to,
sorry.
I was just going to say, if you wanted to convince the string theorist, it might be better to pretend it's 3 time, even if the math suggests something else.
I was very
There-
struck indeed, David, but I'm sorry, I can't remember whether the remark was yours or one of the other participants in the discussion. But to me, the very striking remark about the shadow of non-metricity in the conformal group,
Yes.
which
So
seems to me to
the
be hinting at
scale
something very deep.
transformation.
Yeah, exactly.
Yeah. I mean, the string theorists oftentimes overlook this. I mean, the
And that-
really good ones
absolutely.
don't. The very good ones don't. But yeah. So I mean, I even have I've been obsessed with non-metricity. It's the covariant derivative of the metric. It's literally the geometry of point defects, zero-dimensional defects. So all of gravitation, it's the most fine, it's the smallest form of gravitation possible. It's like a quantum of classical gravitation, if you will. And so to me, non-metricity is the best because you can do everything with it. You can make any one-dimensional defect from an infinite number of zero-dimensional defects. So, or if it was discrete, maybe it would be a finite number, right? So I'm very interested in exploring that, and I've actually identified how to generalize it in the superspace. But I just haven't made like a supermetric affine gravity theory. And spin 4,4 is also very curious because typically they say in arbitrary dimensions, the conformal group and the metric affine group, that metric affine group contains curvature, torsion, and non-metricity. The only way to bring those two together is to go to infinite dimensions. So you have these two finite groups that unify in the infinite dimensional diffeomorphism group. And the remarkable thing that is specifically in D equals 3 plus 1, because of a slew of exceptional isomorphisms, you can actually show that spin 4,4 from the split octonions actually unifies. It contains the conformal group and it contains GL4R and AL4. Well, if you go to spin 5,4, then you certainly get translations as well, because
That's
spin 4,4, and when you break to spin 3,3 cross spin 1,1, that's isomorphic to GL4R because SL4R is spin 3,3, as Robert Wilson is very familiar.
That's extremely interesting. I'm wondering if there isn't a hint of that already coming out of the way that GL4 kind of appears in the periodicity of the structures in the Bok periodicity and the Clifford algebra approach.
Yeah, exactly. I mean, the octonions are essential to that. And I should mention that all of
The
this
octonions are essentially Clifford. Yeah, they're further. Sorry, go ahead. I didn't mean to cut across.
I was going to mention that this physics. So we've been talking about 11 plus 3 superconformal algebra, and then we have other work that went into 27 plus 3, and that was all inspired by these algebras, these magic star algebras of exceptional periodicity that combine exceptional Lie groups with Bott periodicity.
Yeah.
And
No,
so there are these new algebras that came out.
Sorry,
and I'm just saying that, that's part of my story, at least, those algebras, because I mean, I just focused on E8, but there's this E8-2 and this E8-3 that they aren't Lie algebras, but they contain spinor representations and
absolutely.
There's
a continuing tower of structure there, which, as I say, whether there's new physics within that the further levels of that tower of structure or not is completely open speculation. I'm way beyond my pay grade, but that there is, my deepest suspicion is, I think somebody actually mentioned that the way that the role of the split octonions seems to suggest deeper duality principles will turn out in the end to be connected with ideas from cohomology. I think some of the very deepest ideas here clues as to how that further the further levels of that tower within the Bott periodicity may indicate new physics will turn out to be connected with ideas coming from cohomology. But that's very handy wavy indeed. However, I was utterly fascinated, well, by everything you said, your entire talk, but especially that last remark, and I'd very much like to correspond with you a bit further about that if you have the time.
Sure, definitely. Yeah, I appreciate it. I mean, I'll just put my email in the chat. Anyone can.
Sure. Well, thank you again for an utterly fascinating talk, and have obviously generated a tremendously, exciting discussion. So, what more can I say?
Yeah,
Thanks so much. I appreciate it.
Totally agree with you, Michael. One last thing, David, you have been mentioning torsion. Have there been attempts to relate torsion, let's say, to the weak interaction? Or, in the sense that
it's very analogous. It's
So
very
Steve,
analogous.
can you say some more?
Well, okay, so there's work by Grant Remen and Clifford Chung. So there's this thing called the double copy, which relates Yang-Mills theory to gravity. And so along that story, people have been thinking about, well, it turns out that GR is kind of like a nonlinear sigma model. So you can rewrite GR as a nonlinear sigma model. And let's just go through history. That was for a theory of pions. And what happened? We said, no, the pions aren't fundamental. There's this deeper gauge theory that gauges the electroweak symmetry that can describe some of this. And so those W bosons are very analogous to torsion because the same exact thing happens. You have spin and then you have isospin, right? The spin density source is torsion. And so you put fermions in curved spacetime. Everyone agrees that you have to have this 4-point interaction between fermions, just as pions have 4-point interactions, right? Everyone agrees that pions have interactions that are actually mediated by W bosons. So there's fundamentally 3-point interactions. And actually these trivalent graphs are like kind of very crucial to this double copy story as well. So trivalent graphs are nice. And so that 4 Fermi coupling, I mean, it's been shown in the literature how that is mediated by torsion as a 3-point term. So in that sense, there's this nice story. I think it really is suggestive that something like Einstein-Cartan theory or any gauge theory of gravity of torsion is a good thing to think about because I think when you study history, it makes sense. Pions are non-renormalizable. GR is non-renormalizable, but Yang-Mills theory is renormalizable. And it would be nice to study a renormalizable theory of gravity, right? That limits to GR at low energies.
It is astonishing, isn't it, that so little effort seems to have been put into quantizing Einstein-Cartan.
Yeah. I proposed this as my PhD project to Zvi Byrne, and he said it was too crazy. Because there was someone who gave a talk who said, hey, well, he wasn't even a string theorist, but the string theorists proved that Joel Shirk and Schwartz proved that the torsion is the same thing as the axion. But I don't know, the torsion's crackpot. So, let's just focus on the axion. So a lot of the scattering
on the contrary,
amplitudes
I think, as somebody was saying earlier in the discussion, I think torsion actually is the key ingredient to understanding how the bare
oh yeah,
could be made.
Very important. Yeah. I mean, it's geopolitics. I mean, the Russians studied it during the Cold War. So what are you going to do?
Ah, yes.
I mean, they put out unified field theories claiming to get Tesla death rays during the Cold War. So obviously it's that's not right.
I have to.
It's funny you should mention that because there was a discussion. There was a little philosophy of physics conference in Oxford the other day in which somebody made the point. I think it was actually to do with Landau. Oh God, I'm sorry. I'm blanking now. But some particular construction that Landau favoured, which Gell-Mann was very opposed to, and it seems to be entirely to do with the politics of the Cold War. It just seems to have been, a dialogue, not quite a dialogue of the deaf, but the actual math and physics seem to become completely hopelessly overlaid with these ideological commitments to do with. Anyway,
so
that's not.
So what is the stumbling block in saying something like Einstein-Cartan theory or some variant? The torsion part is actually the weak force. The curvature part is general relativity, and the torsion part is the weak. So, Bernd, you want to say something on that?
In the original version of the Einstein-Cartan theory, the torsion effects are too weak, so they would only come into play at a length scale well below the weak scale. That's the problem with the original idea. But there was an idea based on if you don't take the Einstein-Hilbert action, but take an action quadratic in torsion and curvature, then you get something called strong gravity. And this really acts a little bit like the weak and also like the strong nuclear force. They have naturally something like confinement. You don't have to put it in by hand. They have really some confinement potential. So this has been tried in the 1970s, I think, by many different authors, by Hale, which was mentioned by David in his talk. These theories, first of all, are quite complicated, so they have a lot of terms and undetermined coupling constants, so the quadratic torsion and curvature theories, and they also have the same trouble you get if you introduce extra time dimensions. So you have ghosts and tachyons, but there are some versions of these theories which do not have ghosts or tachyons, and And
Yeah, I
some,
mean, no,
and-
Bernd, I keep coming back to this point that
Okay.
all along for us, quantum field theory seems to be sacred. And that is where some of these additional troubles come from, like ghosts, tachyons. I'm not sure that above the electroweak scale, we should be working with QFT. It has been tested. QFT has been tested up to the electroweak scale. What's happening about that, I don't know.
Okay, so maybe then people were too early to abandon the theories because they seem to be in conflict with quantum field theory. But this was the main reason why people stopped working on it. And if you go back to the original Einstein-Cartan theory, there was a linear Lagrange function. The main trouble in the 1970s was that they could not quantize it. You have a spin-spin contact interaction like you had with Fermi's theory of beta decay, and they could not find a renormalizable version of Einstein-Cartan theory for Einstein-Cartan gravity. So this is why they did not pursue it any longer. But in beginning at the 21st century, so in the decade from 2000 to 2010, the people working in loop quantum gravity noticed that the classical limit of loop quantum gravity, if you include fermions, is actually Einstein-Cartan theory. So they have to introduce torsion in their theories.
Yeah.
But they're
Likewise,
missing.
supergravity also has
Yeah.
torsion. So yeah.
Can I say very
But-
quickly? This is sorry. Can I just say very quickly that
Of
this
course.
is something which came up in discussion in the Mond meeting in St Andrews, which I was you were asking me about a month or so ago, to Jinder, and the proceedings of which we will very shortly have
Mhm.
online.
What came up there? What came up there?
Precisely the point that that our last speaker has just made about the specific role of torsion in.
Yeah. So since you mentioned Mond, I'm selfishly poking my point. I'm looking at SU2R cross U1 in correspondence to electroweak, and to see if this leads to a renormalizable theory, again in correspondence with electroweak, where SU2R will eventually play the role of general relativity. And U1 is the new fifth force, which seems to have Mond-like properties. So I'm quite excited about it, that Mond and GR might be encapsulated in this SU2R cross U1, which I call GR and dark electromagnetism. Sorry, just selling my work here.
No,
It's
very
Gravity
interesting
couples
indeed.
to
Stuff like that
everything.
sounds very interesting.
Yes, and can I just say super quickly, this I think was going to be one of the themes that I was hoping that Igor would talk about, if indeed he agrees to our invitation to speak, because I know this is something he's worked on. Yeah,
Torsion?
yes,
Yeah.
and the connection with Mond in connection with his own program for pre-canonical.
So he also has interest in Mond. Igor has interest in
Oh
Mond.
yes, very much so, very much so. The latest talk he gave, he gave a talk precisely on.
Why don't we do that then?
Can I just get the sentence out? Sorry,
Yeah.
he gave a talk precisely on the connections between his own pre-canonical quantization program and Mond at the Polish General Relativity Society meeting last week.
Oh, is this
which will also
Konachikov?
be on-
Igor Konachikov?
Yes.
Yes.
Nice. I
Well,
just studied all that stuff. Yeah.
Michael,
There's a
why
link.
don't-
Sorry, let's all try not to talk over one another. I was going to say there will be a link to all the talks at that meeting at the Polish, the Krakow Polish General
great.
Society
The
meeting
Polish
on
meeting
our
is-
site. I hope within the next 3 or 4 days.
Great. So Michael, sorry, I was talking.
No, apologize. Sorry.
I'm so sorry. I'm sorry. How about we try to get Igor and the Korean person on wide binaries, both of them, let's say on the same day, because only one free slot left, and they can have, let's say,
I'm
50,
quite
45
open
minutes.
to that suggestion. Let me do my best. You speak to the Korean. I'm sorry, I'm afraid I don't know the name of the. You mentioned his name.
CHAE. I don't know how to pronounce it. I would have just said Che. Yeah,
Yes.
actually, I'm in touch with him once in a while. I'm talking to him. I personally think his work is very, very important.
Sounds very interesting. But if that's the case, if that's the case, I'm just thinking it might not so naturally fit together with the ideas that Igor wants to present, might it not be possible for us just to have one additional session before the
We
end
could
of the?
do that. Yeah, so Rob has shared the name. It is Q Hyun Che. Q Hyun Che.
Hey,
Yes.
Che. Oh yes, I think
Hyun-
I've come across. Yes, I'm not quite sure
He
how you
was
pronounce
there.
it.
He was there at St. Andrews. He was there.
Yes, exactly. He was there. He was one of the speakers. Kwei Hung Che. Yes, I remember him. Yes.
Say
yes.
the first name. Say the first name.
Well, I think I'm don't put words in my mouth, but I think he's pronounced Kwei Hung Che.
Kyo
Kwei, I think it's pronounced Kwei, but I could be wrong.
Che.
Yeah.
Cool. I'm open to correction. I don't speak Korean, and I wouldn't dream of telling
He deserves-
how somebody else's name is pronounced when I don't know the language. So, but I think my recollection from when he was introduced at St Andrews is that it's Kwei Hung Che. But again, I'm open to correction.
Yeah,
My
he deserves to
Korean
be heard.
is my Korean is not very good, but I think it's along the lines of Kyushin Che.
Thank you. Okay. Well, your
Thank
Korean
you.
is certainly far superior to mine. So because I said I'm more than open to correction on that.
Okay, maybe I go ahead, Michael, and invite him. And
Oh,
if
yes,
we
by
go,
all means.
we do both the talks 1 week after another. Otherwise, we do because I
Well,
think
I see no reason why we couldn't have an additional session.
yes, we could definitely do that. We can do that. Yes. So great. It's
And
not-
obviously, but still preserve or keep all our options open for the for next year's.
Yeah. So Che's talk is not octonions, but it's at least fundamental physics. He's telling us that there's no dark matter and Newtonian gravity is not correct below certain critical accelerations. And I think he deserves to be heard. And
of course, those are both take-home messages from Igor's work as well. So maybe it would make sense to put them together. But let's discuss that further before we come to any. No.
Great, very good, very good. Yeah, I'm so happy we make place for new so-called non-mainstream ideas and actually have great fun in doing that. Yes.
Yes, it's certainly been great fun today. This has been an absolutely exhilarating evening or morning, depending on which part of the world you're in. But thanks again to David, and thanks again. Well, very strong thanks to David. Very strong thanks also to everybody who's participated in such a sparkling discussion. Thank you again.
Appreciate it.
Okay, great. So shall we log out now, Michael?
I think we've come to a natural end, unless there's anybody who wants to add any final remarks.
Thank you to David. That's what I wanted to add.
Yeah. Thanks, David.
Appreciate
Great fun.
We'll see you all in 2 weeks' time.
Yeah, see you at Corinne's lecture after
sure.
2 weeks. So I'm logging out.
About the transcripts, I will see if there's some way of getting those up onto the site so that they can also be studied in addition to the actual video recordings.
Great. Okay. Thank you, everyone.
Okay. Thanks again to everyone. I'm going to log out now, if that's okay.